long time, two opposing views about nature were introduced. The first one is that the universe obeys a fixed law, and everything exists in a well-defined objective reality. And the other one is that objective reality does not exist. All is flux, all is change. As we delve through the chapter 4 of Ian Stewart's Nature's Number entitled The Constants of Change, we will get to know and learn which of these two contrasting viewpoints will be accepted, or can they be both acceptable and applicable at the same time? To start, let me introduce myself. Hi, I am Czeah Ann Alisoso, and here are my group members.
Hi, I'm Hannah.
Hi, I'm Reanna Lyn A. Catayoc.
And I'm Precious.
And this is another episode of Nature's Numbers.
So let's start with the major source of this chapter, from whom the author borrows his contributions to the world of mathematics and science as examples in this book. Sir Isaac Newton. Sounds familiar. Truly familiar. Well, of course, he's the reason why we are experiencing difficulties in mathematics and science, and that we ended up getting low marks even if we have to get our brain cracked. Joking aside, we get to learn about his famous discoveries of calculus, the three laws of motion, and the theory of universal gravitation. It was Newton who opened up the universe to a scientific investigation by insisting that the physical laws that operates the Earth must also operate everywhere else, and that to discover what works on Earth is to discover what works on the universe. Further explanation about this chapter proceeds to the creation and use of calculus by giving diagrams that includes acceleration, the sequence of velocities, and the likes. Let us find out how Newton changed the essentially static model of nature through his theories, as we explain and elaborate on the constants of change.
To start, we first try to look at theories that essentially offer the mathematical static model of nature, the Ptolemy's theory of planetary motion. On page 49 in Ian Stewart's book called Nature's Numbers, the Ptolemy's theory of planetary motion used a system of circles revolving around centers that themselves were attached to revolving circles, wheels within wheels within wheels within wheel. However, at that time, mathematics was thought to be responsible for discovering the catalog of ideal forms used by nature, on the basis of the democratic observation that every point on a circumference of a circle is at an equal distance from its center. The circle was thought to be the most perfect shape possible. Nature, as a product of higher beings, is perfect by definition, and ideal forms are mathematical perfection. And so, the two go together naturally. And it was considered that perfection was thought to be unblemished by change. Now, let's proceed to Johann Kepler. So what's his importance here? Kepler challenged this idea by discovering ellipses instead of the complex systems of circles. However, Newton threw it away entirely, replacing it with the laws that produced them. But first, Newton's approach to motion analysis is simple, which can be illustrated in the motion of a projectile. But Galileo experimentally discovered that a route of such a projectile is a parabola, a curve that is related to the ellipse and is known to ancient Greeks. Here, the parabola takes the shape of an inverted U in this situation. The parabolic path can be most easily understood by decomposing the projectile's motion into two independent components. First is the motion in a horizontal direction and the motion in a vertical direction. According to Newton, there are three mathematical patterns that are determined by a cannonball's motion. First is the height, velocity, and acceleration. So Newton cited that although the position or height of a cannonball changes in a complex fashion, its velocity changes in a much simpler manner, and its acceleration varies in a very basic manner. To illustrate further, the figures show on the first graph that the ball rises and then levels off near the top before falling again, and it comes back to zero, which is stationary. So therefore, the height of the cannonball above ground at 1 second intervals is 0, 45 meters, 80 meters, 105 meters, 120 meters, 125 meters, and then it comes back to 120 meters, 105 meters, 80 meters, 45 meters, and then it ends with 0, which is stationary. Then, the pattern of distance is perplexing, but on the second graph, the pattern of velocity is considerably more straightforward, which begins with the 50 meters per second upward velocity, and then the downward velocity is 10 meters per second. The pattern repeats itself every second. Negative 20 meters per second, negative 30 meters per second, negative 40 meters per second, and then to negative 50 meters per second. Therefore, the cannonball lands on the Earth at this location of negative 50 meters per second. And lastly, for the third graph, the cannonball's acceleration is represented by the following sequence, which uses the negative integers to denote the downward acceleration of motion of negative 10 meters per second squared that is applied to the ball.
Knowing that the acceleration of a cannonball is always 10 meters per second doesn't tell us anything about the shape of its trajectory. This is where calculus comes in. It allows us to move from knowledge of acceleration at any instant to velocity at any given instant. Calculus is a method for dealing with rate of change problems or the derivatives between Newton's law of physics. It provides in particular a mechanism for determining rates of change known as differentiation. These twin calculus procedures, like Janus twin faces, point in opposite directions. Mathematicians have been now fascinated with the relationship between human behavior and the laws that produce it. God is a mathematician, Paul Dirac said, suggesting that nature itself is mathematic. Just as change in nature can be described by mathematical processes, so can form in nature. The laws of physics are equations for various rates of change. For example, the heat equation is all about the rate of change of a conducting body's temperature. A rate of change is about the difference between a quantity now and a value in an instant future. Equations of this kind are called differential equations. All have the same origin. Ever since Newton, physicists have tried to describe the universe in terms of differential equation. The word solve means to find a precise mathematical formula that describes what a system does. Isaac Newton's Principia Mathematica sought to work backward from behavior to laws. He began with Kepler's discovery that planets moved in ellipses and worked his way up from there. So how did this come about? What of the two-body problem? Well, physicists know that the two-body problem was only solved through Newton's time. Using his law of physics, he was able to use calculus to understand the changes in motion, position, or even acceleration between two attached bodies in the universe. Some of the processes involved is embracing change itself. Surprised? Well, not until you hear this. There are simply too many variables to solve the three-body problem to create a doable or general equations that governs its natural system. So what Newton did is, he simply, as mentioned briefly earlier, he changed the meaning behind solve to simply finding the approximate numbers. Henceforward, this resulted in Newton's resorting to the process of induction rather than deduction, in which he discovered, as Ian Stewart would say, a beautiful result.
According to Stewart, Newton found that the necessary force should always point in the direction of the sun, and it should decrease from the planet to the sun. Moreover, this decrease should obey a simple mathematical law, the inverse square law. This means that the force acting on a planet at, say, twice the distance is reduced to 1/4, and the force acting on a planet at thrice times the distance is reduced to 1/9, and so on. From this discovery, it was a short step to the realization that it must be the sun that causes the force in the first place. The sun attracts a planet, but the attraction becomes weaker if the planet is farther away. Using induction into the laws that govern force, he was able to deduce the motion of the two-body problem with inverse square law, as the two attracting bodies, or planets, let's say the sun and either one of the terrestrial bodies of the universe, are implied to move in ellipses about their common center of mass. As Kepler again puts it, while Mars moves around the sun in a giant ellipse, the sun moves in an ellipse so tiny that its motion goes undetected. Indeed, the sun is so massive compared to Mars that the mutual center of mass lies beneath the sun's surface, which explains why Kepler thought that the Mars moves in an ellipse around the stationary sun. However, even when we can say that the general equation that Newton has come up for the two-body problem is revolutionary in its own right, it doesn't mean that it can be applied to just about anything in the universe. One example of the discrepancies detected was evident when few of the succeeding scientists after Newton tried to solve the three-body problem. Now, the three-body problem was kind of a big deal since it does not only describe the motion of the sun and each of the terrestrial bodies in the universe like the Earth, it also delves deeper into the motion that includes the moon. This may all sound promising, yet the issue is the three-body problem is integrable as proved by Czeah in 1994, unlike the two-body problem. This leads to him showing that such a system can even exhibit a strange phenomenon such as Arnold diffusion, which was first discovered by Vladimir Arnold in 1964. Arnold diffusion essentially produces a drift in the relative orbit, which is an example of what is commonly known as chaos. Notice that this approach again changed the meaning of solve. First, the word meant find the formula. Then its meaning changed to find approximate numbers. Finally, it has in effect become tell me what the solutions look like. These tenets of our sciences, especially the three-body problem, only proves that quantitative answers are not enough. Hence, when we fail at approximation, we then resort to qualitative answers.
This brings us to our final question. Why all this fuss? Why do we need formulas anyway? Simple. Even if there is no such thing as constant, change is. And to truly appreciate and understand these constants of change, explanations must be simplified and rationalized. Thus, we arrive towards numerical rules and equation in our journey to discerning our nature's numbers. As Heraclitus once said, the only constant in life is change.
Thank you.